Okay. Hello, everyone. Welcome back to the Machine Learning Summer School 2020. So today it's my pleasure to introduce our next speaker, Moritz Hardt. So Moritz Hardt is an assistant professor in the Department of Electrical Engineering and Computer Science at the University of California, Berkeley. So he investigates algorithm and machine learning with focuses on reliabilities, validities, and societal impact. After obtaining a PhD in computer science from Princeton Universities, he held position at IBM Research, Google Research, and Google Brain. He also a co-founder of the workshop on fairness, accountability, and transparency in machine learning, and co-author of the textbook Fairness and Machine Learning. He has received an NSF Career Award, a Sloan Fellowship, and Best Paper Award at ICML 2018 and iClear 2017. So without further ado, Moritz.
Yeah, thank you so much for introducing me. I really appreciate the opportunity to speak here. And I will share my screen now. Let me see. There we go. Are you seeing my screen now? Excellent. All right, so thank you so much for joining me to this talk. I want to give you a little bit of a tutorial on fairness in machine learning and some of the limitations and opportunities of using machine learning in the context of consequential decision-making. I will split that across two parts. The first one is today, the other one is coming up on Thursday. I'll tell you what I'll have planned for both days. So it's a tough topic to engage with. It's a difficult topic, and it's hard to even say where to start. And I think it helps to acknowledge that we live in a world of pervasive inequality and oppression and discrimination. And current political events certainly are testament to how grave that situation is and how urgent it is to act. And as we use machine learning to formalize, scale, accelerate processes in this world of inequality, we run danger of perpetuating existing patterns of injustice. Okay, so we have to be careful in the way that we use machine learning for problem solving in a world that is very unequal and has a lot of existing injustice. But I would say that there's also a somewhat fragile opportunity to revisit decision-making and revisit how we do machine learning in various domains and reform existing processes, possibly for the better. So I'm hoping that machine learning can also be a tool that is part of the reform here. And I would like to say that, in some sense, my tutorial is not even the right place to start. I would say you should start by reading the important scholarship that points out the potential issues with using AI and automated decisions. And there's been tremendous scholarship. Just to give you 5 books that appeared in recent years by Ruha Benjamin, Meredith Broussard, Virginia Eubanks, Safia Noble, and Kathy O'Neill. And all of these books give you a tremendously important accounts of the dangers of using AI and computer technology for solving problems that have societal impact. And these are the books that you should start with to get a sense of what the dangers are. And there's a lot of important scholarship. You should also check out tutorials and keynotes given by Joy Bolamwini, Kay Crawford, Timnit Gebru, Latonya Sweeney, Meredith Whitaker, and others that have done tremendous work in this area and have given a very accurate and important accounts of the dangers of using this technology. And so this is, in some sense, the natural place to start. And my tutorial, though, And let me maybe give you one quote that I find fascinating from Ruha Benjamin's book. So she introduces something she calls the New Jim Code, and she calls that the employment of new technologies that reflect and reproduce existing inequities, but that are promoted and perceived as more objective and progressive than the previous systems of than the discriminatory systems of a previous era. So this points out, that machine learning can have, and AI can have, sort of this effect of being perceived as more neutral and being perceived as more progressive than the old bureaucratic processes that constituted blatant discrimination. But in the end, it just reproduces these inequities. And she gives a powerful, persuasive account of that danger. So with that said, keeping that in mind, the focus for this tutorial is primarily on discrimination in consequential decision-making settings. So I'll be talking about decision makers that have to make typically a binary decision, something like accept or reject, in a setting that is has consequences for the individual. Hiring, college admissions, applications in criminal justice, and so forth. That's the kind of setting you should think about. And I should say that this excludes right off the bat many other forms of injustice or even unfairness that exist in the world. And not everything that is a form of injustice is discrimination in a decision-making setting. Okay, so this is already limiting the scope. The second caveat is that I'll be talking primarily about or from a US-centric perspective, especially so far as my examples in the legal backdrop go. And I appreciate that this audience is geographically very diverse. We have a lot of a strong European audience here and people from all around the world. And so my examples do not necessarily apply to the societal and legal framework in your communities. And this is a limitation, but the legal situation is so fragmented and that it doesn't make sense to talk about this problem of discrimination sort of globally. It takes on very different forms in different countries. And so finally, of course, I will be talking about formal models and frameworks to address these questions. That's because that's where my expertise is, but that is not in any way meant to just decenter or distract from the scholarship that I just mentioned. That still stands and is important to keep in mind. It also decidedly leaves room, at least in my opinion, for non-technical interventions. So things that are not, using prediction or machine learning to solve a problem. So we will, in the course of this tutorial, encounter scenarios where many of you will be challenged to, ask the question, should we be using prediction or machine learning in the first place to solve this problem? Okay, so that's the focus for this tutorial. And I see there are some questions. So maybe if you have questions already at this point, I can take one of them, if you will. Let's see. Okay, maybe there are no questions here. Okay, so some of you might come to this and say, well, isn't discrimination, and this was some of the early reactions to this topic, isn't discrimination the whole point of machine learning? Isn't it the whole point to draw some decision boundary and, label some of the points accept and some of the points reject? And that's going to exclude some people and include others. Isn't that the whole point of machine learning? So wouldn't it be a little bit rich to accuse machine learning of sort of constituting or participating in discriminatory practices? And so the concern that we'll trace in this tutorial is with an unjustified basis for differentiation, not just any form of, distinguishing or between individuals, not just any form of, accepting or rejecting individuals in a certain setting. Okay, and so unjustified basis for differentiation could be something like practical irrelevance, like in the context of sexual orientation and employment decisions. We don't think this is practically relevant for the job, so why should it be part of the hiring decision? But there's also a more complicated notion, perhaps, of moral irrelevance, where you might have something like disability status, and that accommodating somebody's disability might incur additional cost to the employer, but we decided as a society that this is a cost that the employer has to absorb, and we consider it morally irrelevant that somebody has a disability when it comes to hiring decisions, even if on purely statistical grounds that might affect their work. Okay. Similarly, the possibility of pregnancy should not have an influence on hiring decisions, even if it might offset the number of hours you can work in the future. Okay, so these are examples of moral irrelevance, and this is the sort of thing that discrimination is trying to capture. And it's important to understand that discrimination is not a general concept. It's domain specific. Okay, so it doesn't apply to every domain. It's trying to sort of talk about domains that are concerned with important opportunities that affect people's lives, not just any, it doesn't apply to any frivolous example of or use of machine learning. So it applies to these consequential domains. And it's also group specific. It's about socially salient categories that have served as the basis of unjustified and systematically adverse treatment in the past. So race, gender, disability status, these are things that have been used or have been discriminated against in the past and continue to be a focus of what discrimination means. So it's not just any group membership, not just any group status that we're concerned with. And so this is where the law comes in, and I'm going to give you just like a very brief, sense of what the law does and doesn't do, just as a framing. In the United States law, there are regulated domains that have some kind of anti-discrimination legislation, and others that don't. Credit is an important one, and there's the Equal Credit Opportunity Act. There is education with the Civil Rights Act of 1964. Employment, housing, and public accommodation. And these are all private sector domains. These leave out government domains where the law might be more complicated. And one important thing for machine learning, because a lot of the applications that we do are, perhaps the main application of machine learning right now is advertising, at least when it comes financial incentives. And these regulated domains extend to marketing. So if you're advertising for a credit card, or you're advertising for a hiring ad, then these regulations extend to the advertisement. Okay, and again, I leave out all sorts of government laws that also have different rules. And there are legally recognized protected classes in the United States: race, color, sex, religion, nationality, citizenship, and so on. And these came about in different legislations and different, at different times. So it's not like there was just one sort of coherent anti-discrimination statute that came about at some point. These things were hard fought over time through decades of activism, and were often responses to political movements and events like what we now call the civil rights movement of the 1960s. And they continue to be important and relevant and influx these kind of categories. Okay, so just recently, a couple of weeks ago, there was the big Supreme Court decision that said, basically reaffirmed that what I just had on the previous slide, the protection of, or the anti-discrimination law for sex extends to gender and extends to sexual orientation. Which was something that the Obama administration, held to be true, and was sort of in flux under the current administration. And this decision kind of showed that, or reaffirmed that it continues to extend to these domains and protects, gender. Okay, and so. This is an important example to show you that things continue to evolve and are continue to be contentious and continue to be a source of political discussion. Okay, so in the United States, there are two legal doctrines primarily, and I'll state them briefly so that you know when you hear these terms what that roughly means. there are two ways that you can try to show that somebody discriminated against you. One of them is disparate treatment. And disparate treatment tries to capture things like purposeful consideration of group membership. If I actually look at your, your group membership status in one of these protected groups and make a decision based on that, and it tries to capture intentional discrimination even if the group membership is not explicitly considered, but I have an intention, a purpose of discrimination that I'm pursuing. And then there is, and you could say that the goal here is to capture procedural fairness, to capture that, the procedure by which you sort people, it doesn't on the face of it sort of constitute a discriminatory practice. And there's another doctrine called disparate impact, which tries to capture sort of more indirect forms of discrimination and tries to get at things that are sort of avoidable or unjustified harm, possibly indirect. And so the goal here is more distributive justice, or to minimize differences in outcomes. So disparate impact would allow you to argue, even if sort of procedurally this looks okay what the decision maker is doing, somehow down the road there's a big disparity, and you're trying to hold the employer responsible for this disparity that they caused in their decision making. And people have recognized some tension between the two. So, sometimes avoiding disparate impact, so avoiding that you have some kind of disparity between groups down the road, you might want to take group membership explicitly into account. And that is something that it poses sort of a tension between these two doctrines, and that has certainly also been something that the formal work in this area has struggled with. So later we'll see that the some of the fairness criteria that we'll go through make explicit reference to group membership, and as such you can ask if that would be a problem for under the disparate treatment doctrine. So would they constitute disparate treatment? Okay, this is just to give you a sense. I'm not a legal scholar. There's obviously a lot more that's going on here. I just want you to have sort of working grasp of what this looks like. And importantly, there's some caveats about the law that I think are worth keeping in mind. It's not like the anti-discrimination law in the United States reflects one coherent moral theory, and it's just sort of an operationalization of that moral theory. That's not what it is, right? So these legislations were responses to activism, to civil rights movements. Each of them came about over time and was involved many fights, and was some kind of agreement between different political parties, right? And so this is not, it's more fragmented than just one sort of top-down idea of discrimination that takes on different shapes, okay? And in particular, the law does not give us a fairness definition that we could readily formalize or operationalize. So as computer scientists, if we're trying to work with formal models on this topic, we can't just turn to the law and be like, okay, here's the definition, and we just need to sort of formalize this in the right way. So this is not how that's gonna work, unfortunately. Okay. So then, what is the first thing that kind of comes, I want you to understand about this topic? And I think the first thing that the community sort of learned is that there's no such thing as fairness through unawareness, okay? No such thing as ignoring or removing sensitive attributes, hoping that this will somehow, get rid of the concern, okay? So the idea that if you just remove all the things that look like a sensitive attribute, meaning like an encoding of a protected group, remove that from the data, scrub that from your data, and then hope for the best, okay? That goes terribly wrong. And there's the books I mentioned contain numerous examples, and I'll just give you one to give you a sense of this. Here was an article from Bloomberg from 2016 about Amazon's same-day delivery coverage. And so basically what happened is that Amazon rolled out same-day shipping to a bunch of US cities. And if you look at Boston, for example, you will see that there is a single neighborhood that is left out. Okay, so the blue shaded area is same-day coverage. The gray area is no coverage. And this neighborhood turns out to be Roxbury, which is a predominantly Black or African-American neighborhood in Boston. And that was the one neighborhood that was excluded, okay? And so people, looked at these maps and they were like, wait a minute, this looks very alarming because it looks quite similar actually to these old redlining maps. Here's one of Philadelphia, where lending officers had secret maps where they kind of, had sort of scratched out certain areas or colored them red as hazardous here, where you wouldn't do business, you wouldn't give out loans in those neighborhoods, okay? And part of the Fair Credit Opportunity Act is it was to get rid of practices such as this, that you could no longer do this. So people looked at these same-day coverage maps and saw this semblance. And so this is an example of the failure of fairness through unawareness. Amazon almost certainly didn't look at race, and that's also what the article said. In fact, the article said maybe they should look at it. But maybe Amazon, I don't know, I wasn't there, but perhaps Amazon was just trying to predict the number of purchases that would be made in these zip codes or in these neighborhoods. And that correlates with socioeconomic status, which in the United States correlates with race. And so maybe they were just predicting purchases. So standard machine learning problem, purchase prediction, you look at past data, you do your machine learning thing, and then you draw the map, okay? And so this is an example of just using machine learning without concern for these problems will just kind of, lead to, some issues down the road, and you'll run into these kind of outcomes that strike people as unfair, okay? And so things like we don't consider that in our data is never a valid argument. And it bears being very clear about this because as of I think at least 2016, companies would certainly often make this argument that we don't consider that in our data, our models are neutral and so on. Okay. So what should we do instead? Or what have people tried to do instead? If ignoring the problem doesn't work, what else can we do? Okay. And so here's my overview for what I'm going to tell you about. In part one, I'll talk about sort of a standard perspective, or what I call maybe a narrower perspective, and talk about fairness criteria and classification. So we'll talk about a standard decision theory setup and supervised learning, and we'll talk about what kind of fairness criteria people have discussed in the context of classification. We'll see some of the relationships and limitations that they have. And on Thursday, I'll work sort of toward a broader perspective and entertain, in particular, two avenues of research. One is causal models of decision-making and what that can say about fairness. And the other direction is dynamic models of socio-technical systems and how that might lead to a different view of this problem. There's a new message. There's a question from Jan. Should one relate this issue to the very problematic "I don't see color" statement? Yeah, so I think that is definitely related. So this idea of colorblind policies is definitely related to sort of this idea of fairness through unawareness, that somehow if you don't look at somebody's race or status in some protected group, that somehow that makes the problem go away. So yes, I think that is certainly related. So this is a good point maybe to ask more questions about the framing, because I'm sort of leaving the part of giving a little bit of background and I'm jumping into some of the technical material. So if anyone has more questions about this, now would be a good time. I'll give you a moment to maybe type in a question before I move on. Okay, so it seems like there is currently no other question. So let me jump into the first part. Oh.
Yes, so I think just in case anyone has a question, you can raise your hand in Zoom, and then you can directly ask the question. Yeah, but we don't have any question at the moment.
Yeah, no worries. Let me move ahead and go into part one about sort of statistical fairness criteria. Okay, so where did formal work on fairness and classification come from? And computer science is actually not at all the first to study this. And in fact, there was pioneering work in the educational testing communities of people that are concerned with, standardized testing and things like this. And a notable scholar here is N. Cleary, who in 1968 already wrote a paper on different fairness criteria for educational testing. So what it means for a test to be fair. And this is very similar to sort of machine learning because you're scoring people, in the end there's some outcome and you're trying to basically predict somebody's performance. And so there are group differences in testing. That's where this first surfaced. There's also early work in economics. Gary Becker wrote his thesis in 1957, introduced the notion of taste-based discrimination. Phelps and Arrow in the 70s wrote important work on statistical discrimination. And those ways of thinking about discrimination in terms of taste-based discrimination and statistical discrimination are still very much the way that economists conceptualize some of these questions. And so this is some of the early work. Computer science joined mostly post-2010. Some early work, in 2008, 2009 maybe, and then an explosive increase in work since 2016. So in 2016 is sort of a tipping point where computer science, I think, embraced this problem of fairness. It became like a major topic at our conferences, and people started working on this very broadly. So you might ask, why today? And why didn't this work back then already solve these questions? I think today we're seeing a different urgency, scale, and reach of algorithmic decisions, and maybe they're going, the idea of making algorithmic decisions has gone much further than we initially thought. And so right now we're confronted as machine learning researchers and engineers, we're confronted with making these decisions, normative judgments about how certain things are supposed to be done, and we're not that well prepared to make these judgments in a lot of cases. So that's why this is kind of an urgent problem right now. And you could ask, why study this in the context of machine learning? Why machine learning and not decision theory or economics and so on? And these fields also study that and should continue to do so. But machine learning fuels a lot of the adoption of algorithmic decision making, and as such motivates some new technical problems. But importantly, this is sort of where rubber meets the road, right? This is where kind of these problems come up, and as a result, we're forced to grapple with them. Okay, we can no longer ignore them. So let me remind you of just a standard formal prediction and decision-making setting. This is just standard decision theory. So you have data described by covariates X. Think of that as a random variable. X could be multidimensional. Doesn't have to be a single thing. Could be like an array of features if you want. And there's an outcome variable Y, often binary. And most of my examples are going to be binary. And that's sometimes called a target variable. And the goal is generally to predict Y given X, okay? To assign a label to X that agrees with Y, okay? So X and Y are both random variables in the same space. And typically we use supervised machine learning to produce a score function R that is a function of X that becomes a new random variable. I call it capital R, the score function, to kind of summarize these covariates into a single real valued score. And then we make binary decisions according to the threshold rule D, which just says 1 if the score is above some threshold and 0 otherwise. Okay, so this is you're thresholding the score in the end. And if somebody's above the threshold, they get accepted. You can interpret 1 as acceptance, 0 as rejection, below the threshold, you get rejected. Okay, so this should strike you as very familiar. And these are random variables in the same probability space and define a population over typically individuals in the settings that we'll be concerned with. So where do score functions come from? This is the, what many others in this workshop in summer school are talking about. Score functions could come from some parametric model of the data. It could be like a likelihood ratio test. That's sort of where a lot of the decision theory is about. So if you have a parametric form for the data, you can come up with your score function that way. You could consider non-parametric scores such as the base optimal score, which is just the expectation of the target variable given the data. That is what's called the base optimal score, or at least base optimal under the squared loss. And that's an important score function that I'll sometimes make reference to. And most commonly, so these score functions are learned from labeled data using supervised learning. Okay, so use any of these techniques that people have, deep learning, whatever, and you come up with a score function that minimizes some loss function on a set of labeled training data. For the purpose of this talk, how you get the score function is not the focus of this talk. So the focus of this talk is what you do with it, the decision part. Okay, so we'll mostly talk about decisions and not about the training process. So we'll forget about optimization and regularization. We'll even forget about generalization, because we'll talk about the population level. Okay, so I'm writing these random variables because I'm talking about everything at the population level. I'm not talking about the finite sample issues. I'm not talking about the difference between population and finite sample. Okay, so I'm talking about decisions at the population level. And so when it comes to decision making, there's the standard confusion table here, where you contrast the outcome that could either be 1 or 0 with a decision that could also be 0, 1. And if both are 0, you call that a true negative. If both are 1, you call that a true positive. These are sort of your good cases where you did it right. And the wrong cases could be a false positive, where the outcome is 0, but you declared it to be 1, so that's a false positive. And it could be that the outcome is actually 1, but you declared it to be 0. That's a false negative. You said negative when it was actually a positive instance. Okay. Oops. Okay, this is a copy and paste error. This disparate impact was a copy and paste thing. Forget about that. What I want to say is that there's something called the true. This is so confusing. I'm just gonna erase that and go back to the presentation. And once you have defined these, you can talk about rates. You can talk about the rate of making positives, true positives. That's the probability that the decision is 1 conditioned on the outcome being 1. You can talk about the false positive rate. That's the probability of making a 1 decision given that the outcome is 0. Similarly, the true negative rate is the probability of a negative decision given a negative outcome. And the false negative rate is the probability of a negative decision given a positive outcome. So these are the 4 possibilities here on this confusion table. And these are 4 natural ways of, natural statistics derived from this table. You could think of these as kind of normalizing by the rows. So these are sometimes called the row-wise statistics, because they talk about the rows of this confusion table. So in your numerator, if you will, you're talking about rows of this table. Okay. That's the standard picture. And so what do statistical fairness criteria do? So far, we haven't talked about, this was just standard decision theory. We haven't talked about fairness at all. How does fairness come in? The simplest way that people have sort of tried to work fairness into the picture, or at least group differences into the picture, is to introduce an additional random variable A that encodes membership status in a protected class. So A could be some encoding of race, some encoding of gender or disability status, and so on. Never mind how you encode that, and that there may be harm to such encodings in the first place and collecting such data in the first place. But you introduce this random variable A. It could be correlated with X. It doesn't have to be independent of X. It could be part of X even. It could be part of the features that you already have. You just give it another letter, okay? You just introduce another letter for it. And then what you can do once you have this group membership, you can talk about different statistics, different statistical quantities involving group membership. And then you can talk about group differences. You can talk about how these statistical quantities differ by group. Okay, and that's exactly what people have done here. So the idea dates back to, like I said, at least the 1960s with the work of Anne Cleary, who already did exactly this. So it's equivalent to what she proposed back then, to look at these group differences, statistical group differences. And we'll review 3 common criteria, and I'll walk you through them. And almost everything that's been done is related in one way or the other to one of these 3 criteria. Okay, so if you understand these criteria, typically if you see something in the literature, you can morally relate it to one of these 3. Maybe not necessarily formally, but it'll be at least conceptually related to one of them. The first one that comes to mind, and this is, I'd say, the most common one, is equalizing the acceptance rate. Okay, so you can simply say that for any 2 groups A and B, we're going to require that the rate of making positive calls in that group is equal in all groups. Okay, so the rate of positive acceptance or acceptance decisions should be the same in all group. Okay, if one group has an 80% acceptance chance, every other group must also have an 80% acceptance rate. Okay, so the acceptance rate is equal in all groups. You can generalize this by requiring that D is statistically independent of A. I'll sometimes just call that the independence criterion. So you can convince yourself that if the decision is independent of A, then these conditional probabilities will all work out to be the same. Okay, so you can just do the math in your head probably. If D, the decision, and the attribute A are independent, then all these conditional probabilities, acceptance probabilities, have to be the same, and you get this. Okay, you can also apply this to the score function and ask that the score is independent of A, and then if you threshold the score, that'll also ensure equal positive rate. So these things are all closely related. And you can ask for, if you ask for the score being independent of A, I find that a very natural way of stating it, and that implies all these other things. And again, there are all sorts of variants, relaxations, equivalent formulations that people have proposed of this criterion. So let's start with stress testing this criterion a little bit. So let's try to think about situations where enforcing this criterion or asking for it does not rule out unfair practices. So where a decision maker could hide blatantly unfair, in some intuitive sense, decisions, while satisfying this criterion. And the example I like to give, and there are other issues with it, but the example I like to give is that you could make good and informed decisions in one group. Maybe you have a lot of experience with one group and not the others. And so you make poor, arbitrary, random decisions in another group. But you do it in such a way that you match the the positive rate. Okay, so you could say in this majority group, you're doing what you've always been doing, and you have a lot of experience for what you're doing. And in some underrepresented group, you just toss a coin and select random folks. And this is not, I'd say this can happen naturally on its own if you have less data or poor data in one group. And so your model is basically not working well on that group. Let me give you an example. There's something called the Framingham Risk Score for coronary heart disease that was created on a cohort of white men, I think at the beginning of the 20th century, if I recall correctly. And then it was used for other patients, and its performance was much worse for other patients. Okay, and so this idea of making poor decisions in one group and good decisions in another is, of course, concerning. And the moral intuition here is that you shouldn't be able to match true positives in one group with false positives in another, right? I shouldn't be able to say, oh, in this group, I have lots of true positives, and I'm making up for it by having lots of false positives in the other group. Because, if you accept, random instances, presumably you're not selecting the best instances that you could, selecting the best people that you could. And as a result, you're sort of setting up a poor track record for that group. Okay. So I think this is an issue with that kind of criterion. I should say, nonetheless, this criterion is very popular and there's a lot of work on it. There was, in particular, one thing I want to mention is work by Rich Siemel and others on fair representations, where roughly speaking, the goal is to use, deep learning tricks, such as adversarial learning and other things, to train a representation of the data that is independent of group membership while representing the original data as much as possible. Okay, so you start from some kind of feature representation X, and you try to get another feature representation called a Z that's as representative as possible of X while being independent of group membership. And so people sort of think of this as kind of data debiasing, and there are some issues with that notion that we'll return to in a moment, but there continues to be a lot of work for it. What I want you to sort of keep in mind is, when you see one of these papers that says, oh, fair representation learning or something, ask yourself, what is actually the fairness criterion that's being achieved, okay? And the underlying fairness criterion doesn't get better by using deep learning, okay? So just because there's a lot of machinery and a lot of apparatus in achieving this criterion, that doesn't necessarily mean there's somehow, it's more fair or there's something more to it than just, independence, okay? So under the hood, it's still the same independence criterion that you saw. Okay, so there might be a question. So the question from Martin is, for binary decisions, is having different acceptance thresholds for different groups enough for this criterion? Yes, so this is a good question. In particular, an easier way to achieve independence, if you just want independence, you could just accept you could have group-specific thresholds and set them up in such a way that the acceptance rate is the same, right? And so this kind of gets to my point, like, if there's such a straightforward way to achieve this criterion, what are you hoping to get out of the more sophisticated way? And maybe try to be specific or precise about what this is. And I think, some of these papers do a better job at this than others. And I like Rich's work. So this is not specific to the initial work here, more of a general point about this line of work. There's another question. Equalizing acceptance rates seems like equality of outcome. Yeah, under some notion of equality of outcome, I think you're right, but we might, I think equality of outcome could mean different things. And I don't want to necessarily use that terminology because I already use outcome variable for Y. So I don't necessarily want to phrase it that way, but I think you probably have the right thing in mind. So that seems good. So okay, let me move on. So recognizing this issue of trading off false positives with true positives, which seems concerning, it seems to violate some moral intuition, people proposed another set of criteria which equalizes the error rates. Okay, so it specifically does not allow you to trade true and false positives. And it will require that all groups have the same false positive rate and all groups have the same false negative rate. Okay, so these rates have to be, these two rates have to be the same in all groups. Okay, and again, you can generalize this, which is kind of nice. You can require D, the decision, to be independent of A, given the outcome variable Y. Okay, so instead of having just independence, you now have a conditional independence. That's one way to generalize this. It also makes sense for score functions. Again, you can require R to be independent of A given Y. And again, if that's what you require, all these other things follow. So if your score function is independent of A given Y, you get that for the decision if you use the threshold rule, and you get that for the false and true positive rates as well. Okay, so this is maybe the most simple and general way of stating this. And so one thing to realize about error rate parity, which makes it a little bit tricky, is that it's a post-hoc criterion. So let me explain what that means. So at decision time, when you need to actually say yes or no, the decision maker doesn't know who is a positive and who is a negative instance. Okay, so they cannot evaluate at decision time these kind of error rates. They're unknown to them. Okay, so in hindsight, somebody can collect a group of positive instances, people that have turned out to have a positive outcome and people that have turned out to have a negative outcome, and you can do that in each group. And you can see, you can look at how they were classified. So after the fact, with the benefit of hindsight, you can, test these error rates, but you can't do that ahead of time, at decision time. And so group differences, or error rate differences are sort of, in this kind of audit setting where you, after the fact, you look at the decisions, often strike people as unfair. So again, there's some strong moral intuition here that, well, wait a minute, if all these, positive instances, people with a good outcome ended up or were actually classified negatively, at a much higher rate than another group, that might seem unfair. Okay, so it seems like one group, if this criterion is violated, it seems like one group would bear a disproportional burden of uncertainty. So it would bear sort of the brunt of these, statistical, errors, and more than other groups. Okay, and so in some sense, maybe a different way of stating this is that you want the harm or the disadvantage from misclassification, you want that to be the same in all groups. You can visualize this using the RC curve. The RC curve is a simple way to talk about threshold rules, where you plot for every possible threshold from between 0 and 1. Let's say your score function is between 0 and 1. You plot the true positive rate, you plot the false positive rate. That typically gives you, a curve. You can plot these curves for each group, or a curve that looks like this. You can plot these for each group. So this is the true and false positive rates that your threshold rule achieves in each group. As you slide the threshold, you trace out these curves, one for each group. And what error rate parity tells you, or what this criterion would tell you, is that the RC curve of your score, if it satisfies this criterion, must be under all the curves. Okay, so the area that's under the intersection of all these curves, these are the trade-offs between true and false positive rate that you can realize while satisfying this criterion. Okay, so this is the thing that you can achieve. And so one interesting point about this is that if you look at this, let me see if there's a question. David is asking, for something like hiring, it seems like you would not have the ability to evaluate these counterfactual, even in hindsight. Does this criteria not make sense in such settings? So that's a great question. David's pointing out that sometimes, we simply, if you don't get accepted, we simply do not see, your outcome ever. We just have no record of it. Let's say if you don't get into Harvard, we never know what your GPA at Harvard would have been. Okay, and so that's an important point. And the answer is yes. So if people do this for lending, or yes, this is an issue that you need to address. So if you do this for lending, for example, people will try to estimate these error rates by saying, well, you were turned down by this bank, but you got a loan with this other bank, and you paid back your loan with that other bank. And so you probably would have also paid it back with that first bank that turned you down. And so that gives us a sense of, how we can estimate these things. But yeah, in general, these things are, like potential outcomes. You only observe one of them, but not both. And so in general, these can be hard to estimate. That's a good question. Okay, so returning to this image of these intersecting RC curves, one thing that you see is that, if you enforce this criterion, that might imply that in some group, you're not doing as well as you could. Okay, so it means that somehow you're actually making the decisions worse for some group. Okay, and this is, I think, a valid concern with this criterion, that it could mean you're doing more poorly in some group just because you want to equalize the error rates. And then that could constitute, harm against that group, okay? Because you could be doing better, and so that is somehow unjustified, that you're harming them in sort of doing worse than you could. Okay, so that's the story about error rates. And again, like I said before, returning to this this confusion table, you could also talk about what happens when you swap, the conditioning. So instead of talking about these row-wise criteria, you talk about column-wise criteria. So you could equalize expressions of the form probability that y equals something, given that the decision is something and that the group is something. Okay, so this is, you're swapping y and d. Now y appears in the argument and d appears in the condition. Before it was the other way around. So you could swap this conditioning. These are called column-wise rates, and they're also statistically meaningful. Specifically, the two standard column-wise rates are false emission rate and false discovery rate, depending on which setting of y and d you choose here. And these are two important things that have been studied in statistics. And you could again say, okay, what fairness criteria do you get when you equalize those? Okay, so syntactically, there's nothing wrong here. You could do that as well. But there's something closely related that people do instead, which is, I'd say a bit more natural and has sort of gained more traction. And that's the idea of calibration. So let me tell you what calibration is. So a score R is calibrated if the probability that you see a positive outcome given score value little r is equal to little r. Okay, so what that means is you can pretend your score is a probability, although it might not actually be one, and certainly not at an individual level. But on average, your score, behaves like a probability. So if you see somebody with score value 0.8, you know that they have a positive outcome rate of 0.8. Okay, so if I know you have, if I see your heart disease risk score is a 0.9. then I know you have a 90% chance of heart disease among people, on average over people with a score of 0.9, okay? So, and then you could ask that your classifier is not just calibrated on the whole population, but calibrated within each group, okay? So you can require this stronger condition that you satisfy calibration in each group, okay? So you throw in an extra conditioning on the group, and you want that your score behaves like a probability within each group. So even if you restrict your attention to a specific group, you know that within that group, your score says or means what it claims to say. Okay, and so if you think about it, you can again show that this kind of calibration by group follows from a conditional independence statement, and that statement is why the outcome variable is independent of the group membership, conditional on the score. So a different way of saying that is, for the purpose of predicting the outcome, your score contains everything you need to know about the group. Okay, so in other words, if my only goal is to predict y, the outcome, then after observing the score R, I have no interest in also soliciting your group membership. And so that's a very natural guarantee that, if I know your score, I don't need to ask what your group membership is. So if I see you're a 0.7, that means the same thing in all groups. I don't have to ask, hey, also please tell me your group membership. And if your group membership is this, I'm going to add 0.1. If your group membership is that, I'm going to subtract 0.2, right? I don't need to do those mental gymnastics. I know that the score means the same thing in all groups. And as a result, calibration is an a priori guarantee, okay? So the decision maker sees the score value R, and at decision time knows that based on this, what the frequency of a positive outcome is. Okay, so score 0.8 means an 80% rate of heart failure on average over people who receive score 0.8 within each group, okay? So you don't need to solicit group membership. But let's not get carried away by calibration. It's not meant to be, sort of a guarantee about individuals. Okay, so just because Mary gets a score of 0.8 doesn't mean that Mary individually, like conditional on her exact features, has a heart failure chance of 80%. That's not what it means. It just means on average over people that receive the score 0.8, the frequency of positive outcomes is 80%. Okay, so that's calibration. Another thing that you should be aware of is that group calibration and calibration in general often follows from unconstrained learning. Okay, so it's not necessarily a constraint on machine learning. It's often what machine learning gives you in the first place. Okay, so there, is a theorem that says under some conditions, the deviation from satisfying group calibration, so how far off you are if you want to relax that, is upper bounded by how good your score is relative to the Bayes risk or relative to the Bayes optimal score. Okay, so if you compare your score function, your learned score function to the Bayes optimal score, the difference in performance will give you an upper bound on the violation of group calibration. So the better you are at machine learning, the closer you are to the Bayes optimal score, the better, the more your group calibration is satisfied. Okay, this is from work with Lydia Liu and Max Simkovitz from a couple of years ago. And so in other words, you shouldn't be surprised to see calibration follow approximately from unconstrained supervised learning. And here's a picture. If you just run logistic regression on the UCI adult data set, out of the box, just no tuning or whatever, you will see this calibration plot. Okay, so if you look at the score deciles from 1 to 10, and you look at the rate of positive outcomes, you will see that these are basically both diagonal lines for male and female, which means that if it were perfectly calibrated, you'd see a diagonal line, and this is pretty close to it. There's another question from the chat. The question is, how does the score calibration link to problems of moral relevance? We could be equally calibrated, but people of a group could end up being worse in reality. How do we adjust scores for this? So this is a great question. That's exactly, and I like the way you think. You already internalized this idea of moral relevance. So one example that can show you an issue with calibration, and I think it's also just an issue with optimal learning, right? So optimal machine learning is always calibrated, right? The Bayes optimal score is always calibrated. So here's an issue, potentially an issue with an optimal score. Let's say I want to predict productivity in the workplace, and I define productivity as the number of hours you work in the next 10 years. And I'm so good at machine learning that I, in fact, give you the exact optimal Bayes score. Okay, so I know the exact expectation of the number of hours you work conditional on your features. And so the issue with that is that somebody who has a disability or somebody who might become pregnant in the future might have a lower score simply because your score correctly identified this loss of work hours in the future. But this is something we deem morally irrelevant to hiring, right? So again, this is a good example of where group calibration doesn't solve this problem of moral relevance, right? Generally, optimal prediction does not, okay? So optimal prediction will use whatever it can. If, a piece of information gives you a boost in predictive accuracy, it'll include that, even if as a society we deem it irrelevant. Okay, so that's a great question. Another thing I should say about group, about all these group fairness definitions, and this is not specific to calibration, but it holds for all of them. If you ensure fairness criteria between two groups, that can lead to violations, and often more striking violations within one of these groups. Okay, and so this motivated work on ensuring group fairness, and there were two papers that started this line of work, one by Kearns, Neil, Roth, and Wu, and the other by Herbert Johnson, Kim, Reingold, and Rothblum. And so one of the illustrative examples from Kearns et al. Is the following made up situation where you have two groups, blue and green, and you accept the same fraction of individuals in each of these two groups, indicated by these circles. And however, in one group, you only accept male candidates, in the other group, you only accept female candidates. And so if you now look within these subgroups, you get a terrible violation of the independence criteria. Okay, and you could imagine examples for all the other criteria as well. And I'd say this is a real concern. The UPenn group around Kearns calls this fairness gerrymandering, and I like that expression. I think this is a real concern. If you enforce some constraint, usually machine learning will satisfy this constraint in the laziest possible way. And so you should not expect to get anything clever, within the subgroups if you equalize some kind of statistic, okay? You probably will see something annoying or something alarming going on in the subgroups, okay? So let's recap where we are. And you know, I have another half an hour. That's plenty of time for where we're at. So let's recap. We saw 3 criteria. And the first of them is, you know, the independence criterion. The second one is this conditional independence of R given R is independent of A conditional on Y. And the third one is, you know, another conditional independence where Y is independent of A conditional on R. And, you know, the first one implies equal acceptance rates, the second one equal error rates. The third one implies calibration by group. So this is the way I like to state them, just because this makes it really easy to, you know, appreciate them in terms of these conditional independencies. And I think you've all, at this point, probably you've had some lectures on graphical models or causality, so you understand conditional independence at this point. So probably this will be also a good way for you to memorize these. And so one question that people asked, you know, once you lay them out, once you lay out multiple fairness criteria, you can ask, can we have them all? So is there a way to maybe, you know, get the best of all worlds and create some amazing predictor that just satisfies these all? And people quickly realized the answer is no. So there's formally, I could state this as any 2 of these 3 criteria are mutually exclusive in general. So except under degenerate conditions, you cannot have them all. And I'm going to just give you one formal statement and exclude the other statements that you could prove here, which is error rate parity versus calibration. The theorem goes as follows. If you assume unequal base rates, so you assume that, you know, the 2 groups have different rate of positive outcomes. So your groups are unequal in terms of outcomes. So currently one of the groups has a higher rate of positive outcomes than another. And you assume that your decision rule is imperfect. Excuse me. So you assume that your decision has non-zero error rates. So it makes at least one false positive and it makes at least one false negative call. And this is the general situation. In general, because we live in a world of inequality, groups tend to have different base rates. And also, you know, typically we don't have a perfect predictor. So our predictors make errors. And under these assumptions, which are the general case, if you satisfy calibration by group, then this implies that error rate parity fails. In particular, if you just do unconstrained machine learning and you get calibration by group, that also means that you by default have a violation of error rate parity. Okay, so enforcing one of them makes the other become untrue. And there's been the initial works here were by Alex Chilichova and Kleinberg, Mulenatan, and Raghavan, who proved similar statements, not exactly this. And then there's been a lot of follow-up work on what if you relax them. And it's not so easy to say what happens in some of these cases when you relax it. And there's possibility that for some of these relaxations, some trade-offs or some non-trivial trade-offs are possible. But what I want to go into instead is how these trade-offs, you know, dominated sort of an academic discourse around an important problem, namely that of recidivism prediction in the United States. And there was a sort of a landmark article by ProPublica called Machine Bias that alleged that there's a software used across the country to predict future criminals and it's biased against Blacks. And this was, you know, written in 2016. I think it came out in May 2016, and it sparked a lot of conversation around this topic. And the essence of the COMPAS debate, at least sort of if you project it to academic circles, what academics talked about, in computer science at least, there was a risk score, you know, called COMPAS, and many jurisdictions in the United States use the score to evaluate the likelihood that a defendant will go on to commit another crime if they were to be released. Okay, so if you have to decide whether to detain or release a defendant that goes up for trial, this is used to estimate the risk of, you know, that defendant committing another crime if they were released. Okay, and judges may detain the defendant in part based on this score. This is not the only thing they look at, but they can use the score. And so ProPublica looked at defendants that ultimately did not recidivate, so ultimately did not commit another crime. And they noticed that of these defendants that ultimately did not commit another crime, Black defendants were much more likely to be labeled high risk by the score than white defendants. Okay, so another way of saying this is that the false positive rate of the score appears to be much higher for Black defendants than for white defendants. Okay, so Black defendants are much more likely to be labeled high risk, even though they do not go on to commit another crime. Okay, and so COMPAS, the maker of COMPAS, called North Point, said, yes, that's true, but our scores are calibrated by a group, and Black defendants have a higher rate of recidivism in the United States, and hence this is unavoidable. Okay, so they were saying, we're just doing our job here. We're calibrating the score. That's what we need to do. If the score wasn't calibrated, the judge would have to do some mental gymnastics around, maybe I have to add 3 points if the defendant is white and subtract one of the defendants Black and so on. And to avoid that, these scores have to be calibrated by group, and that inevitably implies that you get this this disparity. Okay, so this is where kind of this discourse, or a lot of what this discourse was about, for better or worse. And academics were intrigued by this idea that this complex problem seemed to have boiled down to some statistical trade-off that you could approach with mathematical tools and rigor. Okay, so let me add a first word of caution to the COMPAS debate, and then I'll add another word of caution to it. The first word of caution is that both error rate parity and calibration do not rule out unfair practices in this setting. And so it's already a bit of a straw man to argue about, because neither of these rule out things you should actually worry about, okay? And so in particular, what's fair in criminal justice is not settled by appeal to one of these criteria. So we can't reduce the question of justice or criminal justice to one of these criteria. And I want to give you an example, a construction, if you will, to illustrate this point. Particularly, these two properties are not meant to be fairness certificates. They're not proofs of fairness. So let me give you an example of why error rate parity is an issue in this kind of setting. So consider these two groups, and let's say we have two groups, the blue group and the orange group. And our threshold rule is that we detain everyone above a score 0.5, and we release everyone below score 0.5. And our scores are, written here under these stick figures. So they go from 0.1 to 0.7 in the blue group, and from 0.2 to 0.9 in the orange group. And let's further assume that these scores are actually the probability of recidivism for these, individuals. So let's assume that these scores are just the conditional expectation of recidivism given the individual's covariates. Okay, so these are the true probabilities, if you will. And based on these true probabilities, you can compute the detention rate, and you can compute the false positive rate. And you'll see that the blue group has a detention rate of 38%. And the orange group has a detention rate of 61%. So you detain substantially more people in the orange group. So that means independence is violated. These scores certainly don't satisfy independence. And also the false positive rate is much higher in the orange group. So they don't satisfy error rate parity either. So the false positive rate in the orange group is much higher than in the blue group. So you might say, how do we fix this, right? So if you're let's say a police department, and you're accused of like having this detention rate that's much higher in one group than in the other, what could you do about it? And the point of this example is that there are really bad ways of achieving error rate parity, and really bad ways of achieving independence. For example, one thing you could do, you could police the orange group more aggressively, And you could say, we're going to arrest more low-risk individuals in the orange group. So more individuals that have a very low risk of recidivism. As a result, we're going to arrest them, but we're going to release them. And so we're simply padding the number of defendants in the orange group that we're going to release. And if we do that, we simply arrest more people in that group. If we do that, we can actually make it such that the detention rate drops to 42% and the false positive rate drops to 26%. And now these things look like they're similar. So there's a question here that I want to get at. It says there's a Q&A, but I don't quite see. How do I get to the Q&A? Maybe somebody can just send this in the chat. Nothing happens.
I can read the question to you. So how should we choose the right criteria for a specific problem? Any suggestion?
Yeah, how should you choose the right criterion for a specific problem? So this is a good question, and I'm going to return to this in a moment. Let me first wrap up this example because we're in the middle of something, but remind me to get to that, or ask that question again when I'm after this example when I'm discussing sort of the purpose of fairness criteria.
Yes.
Great. So okay, so this is alarming, right? So what this is saying is, if you incentivize someone to satisfy error rate parity, they could achieve this criterion in sneaky ways, in ways that are even much more harmful or introduce additional harm. Okay. So this is not as an incentive, as an objective to pursue. This can be a very problematic criterion. There's also an issue with calibration that's worth pointing out. Again, assume that these are the true probabilities of reoffending. Suppose we know them. This is typically not true, but for the purpose of this example, let's suppose we do it. And let's say we detain everyone above 0.5. And by the way, I should say both of these examples are from a paper by Sam Corbett-Davies, Pearson Fellow-Grill, and Huck from 2017. So they kindly provided these examples to me. Let's say we detain everyone above 0.5. And let's say, we have to satisfy calibration, but I want to release everyone in this group. I just want to give this group a break and just release everyone in this group. One thing I can do with calibration is that I can take a subset of the instances that average to a particular score value. Okay, so here I'm picking out a subset of the instances, 0.1, 0.1, 0.2, 0.2, 0.2, and 0.6, 0.6, 0.6, 0.7, 0.7. I can take all these instances, they average to 0.7. And so one thing calibration allows me to do is this kind of like averaging operation where I take all their scores and I assign them the average value of their scores. Okay, so I replace all of these scores by 0.4, 0.4, 0.4, and these scores are again calibrated. Okay, so this again satisfies calibration, and now no one is detained. Everyone is below the detention threshold of 0.5. So again, there could be sneaky things happening with calibration that are not detected by this criterion. So let me, make this second and sort of more important point about this criminal justice example, and then talk about the scope of this fairness criteria, which was this question. So this is all, this discussion happened. People discussed these fairness criteria at length in the context of criminal justice. And they discuss all these trade-offs and what you can learn from these different criteria. But there's also this question of, are we missing out substantial parts of the problem by committing ourselves to this kind of prediction perspective, this kind of statistical perspective in the first place? Is this not a much more complex problem than what the statistical perspective would suggest? Okay. And so the scholarly debate was around the tension between these fairness criteria. Some rightfully pointed out that there are these feedback loops in policing, and that bias your measurements. You only measure crime where you police, and so that disadvantages groups where you police more. In the United States, that's predominantly like Black neighborhoods, and that's where you collect more crimes, and as well as you start from terrible data to begin with. But that's also not my main point. My main point is, when is the issue not how we predict and what data we use and what objective function we choose, but the problem is that we choose to solve this problem or attack this problem formulated as a prediction problem in the first place. And there's one example I find very persuasive, and this is the issue of failure to appear, and predicting failure to appear in court. That's an important issue, again, in the United States criminal justice system. One approach is similar to recidivism. You could try to predict failure to appear in court. So if you have a defendant and you set a court appointment 3 months from now, and you don't, you want them to show up for their court appointment, and you're wondering if they will. And so one thing you could try to do is, again, do some sort of machine learning and predict failure to appear in court. And there are lots of people doing that, and lots of people pushing for these things to be implemented as part of the criminal justice reform in the country, and to replace, human judges by these, risk scores that fail to predict failure to be in court. And so the idea is, if your score is high, you are kept in jail, and if your score is low, you're released. And because there could be 3 months or more between this event and the court appointment, if you're jailed for 3 months, first of all, that's hugely expensive to put people in jail. Second, it is devastating to the individual. They lose their job, they lose their social ties. It's absolutely disruptive and devastating. And even if they were in a fairly safe, good position to begin with, by the time they get out of jail and they're cleared of their charge, they probably are no longer, and they're struggling to get back. So this is, jailing somebody pre-trial is very disruptive. And so the alternative that I find, compelling is to recognize that people fail to appear in court due to lack of childcare or transportation, due to their work schedules. They might have an employer that doesn't let them go, or simply due to too many court appointments. So there was, at one of the, recent conferences on fairness, accountability, and transparency a couple of years ago, there was somebody who had been in the position of a defendant, a Black defendant, who had 22 court appointments before he was finally cleared of the charge. And so he had to make 22 court appointments. It's not just one, it's 22 court appointments before you're cleared. And if you fail to appear on court appointment number 15, then you are, it's recorded as failure to appear, even if you make all the other appointments. So the issue here is that, if you recognize this alternative, it might make more sense to give people, childcare vouchers or transportation vouchers to compel employers to let people show up for court appointments, and to also work on reducing the court appointments so that it becomes easier to manage this burden. Okay, and you could implement steps to mitigate these issues. None of them have anything to do with prediction. And this alternative is actually part of the Harris County lawsuit settlement. So Harris County is a county in Texas that includes the city of Dallas. And there was a lawsuit against the county that's using these risk scores. And the settlement requires Harris County to provide free childcare at courthouses, develop a two-way communication system, and so on. And so to implement some of these structural interventions so that poor defendants are not, right off the bat disadvantaged and further punished by this system. Okay, and so in this case, I find it very hard to make a case for the prediction for using prediction in the first place, when it seems so much more immediate and important to implement these other steps. So I always found this line of argument very persuasive. And I find it hard as a machine learning person to continue to insist on this prediction thing in light of these alternatives. Okay, so this is where I'm going to return to the question that was asked, right? So what exactly is narrow around these statistical criteria? What makes them limited, right? And so these statistical fairness criteria take the data generating distribution as a given, and they work with nothing but the joint statistics, the observational joint statistics of these random variables, X, Y, R, A, and you can throw in other random variables in the same population, whatever you want. And so as a result, whatever they can tell you is confined to what the joint statistics of the population can tell you. But in particular, you cannot change the population, you cannot entertain sort of hypotheticals, and you cannot intervene on the world that produced this joint distribution. In some sense, it's very reactive. You take everything as given about the world as it is, and you lose a whole range of interventions. And so what I'm going to do on Thursday is, go into this question of, yes, if we recognize that a statistical perspective is perhaps too narrow and rules out too many interventions and just puts the focus in a place where it's not necessarily addressing the right question, how do we take salient social facts and social context into account? How do we go about making our models more aware of the broader questions that are important here? And so this will be subject of part 2 on Thursday. And I'm going to wrap up and then take some more questions. So first thing I want you to remember is fairness through unawareness fails. And so the second thing is a bit of a more nuanced question or nuanced takeaway. I still find these fairness criteria interesting as insofar as they trigger, different moral intuitions. And I think that's sort of an underrated mechanism, right? So I think people often want this kind of fairness definition, and then they're disappointed that these things aren't fairness definitions. They are decidedly not fairness definitions. They're definitely not certifying that something is fair. But they do trigger, and that's just an empirical statement, they trigger these moral intuitions, right? ProPublica was really outraged that this error rate parity failed, right? This is a moral intuition, and it's hard to argue with that moral intuition because it captures something about our moral understanding of how decisions should be made. And so as a result, these criteria can still be applied to surface different normative questions about decision-making and sort of get a better handle on what bugs us about the way decisions are made in a certain setting. And they can lead to these different trade-offs and tensions. And I think that's an important conversation that is not about, let's settle this once and for all, what's fair, what's not fair. That's not what it is. It's a more nuanced, mechanism that's at play here. It helps us discuss, our understanding and our expectations of how decisions ought to be made. Okay, but like I said, statistical fairness criteria on their own cannot be a proof of fairness, and I think, at least within the setup, the statistical setup that I described, I think there cannot be a fairness definition. I'm convinced that there is not a satisfactory fairness definition within this statistical setup. And nor are fairness criteria on their own a good objective function, okay? So as I showed in this example about error rate, parity, and policing, you don't want to make these criteria incentives, okay? So you don't want to incentivize people to pursue these criteria. They can be, if you use them as a gauge, as a measurement device on the world as it is, that's one thing. But if you ask people to optimize for them, that's another thing. So, yeah, there are a bunch of questions. Let me see. So 2 questions, or 3. Okay, questions keep coming in. So that's good. So let me start with Gal's question. Hi, Gal. Thanks for joining the talk, by the way. Aren't you too pessimistic about prediction taking away focus from better interventions? I'm thinking of settings in which we don't know what the right interventions are, and a good estimate of the conditional expectation of y given x may actually help us identify them. For example, in the failure to peer example, it may become salient that women with young children are more likely to fail to appear, highlighting childcare as a better intervention. Yeah, so this is a good point. So, and thanks for asking that question. That's a great question. So I think, when people, like, how did people discover that, lack of childcare is an important factor in failing to appear in court, right? They probably used, statistics somewhere, right? I mean, I'm not making a sweeping charge against the use of statistics, not by any means. I think that would in fact go too far and be too pessimistic. But they probably posed the question very differently. They were asking, let's say, causal inference on what the causes are of failing to appear in court. And it's true that this conditional expectation might somehow feed into that understanding and might give you, or some form of statistics at least might give you a good answer to that question. And it's also possible that simply doing better at prediction, you might be able to look at the model and figure out some salient factors, and it helps you understand that. So I agree with that, but I think that's a bit of a different framing, and we first need to agree that this is the framing of the question that we're going to pursue, and that this is the purpose of why we're doing statistics. And as long as we say the purpose is to simply install these risk scores as a way to sort out pretrial detention, we might accidentally forego the possibility of these different framings of the question. But I think, there will be room for good technical work either way. So I'm not, these other interventions, it's not meant to be like, oh, there's absolutely no interesting research question going on with these things. It's just a reframing of the problem. Next question is by Mirko. Which level of complication is added to the binary fairness criteria in face of multi-class and regression tasks? So one thing I should say is when it comes to these conditional independencies or independence statements that I stated, these directly generalize to arbitrary random variables. Okay, so arbitrary is certainly discrete, and you can work with a little bit of effort. You can also get continuous variables, but certainly discrete random variables, you could have any discrete group membership variable, any discrete outcome variable that takes on multiple labels and so on. And as a result, these conditional independence statements they already apply to multi-class and regression tasks. And that's part of why I like to state it that way. So that's a great question, thanks. Indira asks, what are your thoughts about fairness requirements in settings where prediction is required, say content moderation? Recent research shows that many models flag content with African-American English at higher rates. Are there any fairness criteria that can mitigate biases in these settings where prediction is necessary? Is it necessary evil? Okay, so I was able to parse that. Okay, so that's a great question. So there are scenarios where simply for lack of human resources, we need to resort to some form of algorithmic moderation or content curation. Let's accept that premise. I mean, that's maybe a different debate to have, but let's accept that premise. And yes, so I think, a lot of things like toxicity classification, sentiment classification, abuse classification and so on suffers from terrible biases against, let's say African-American speakers due to correlations in the training data between, words that they use or, phrases that they use that would be scored, in a way that makes them more likely to be flagged. And this is a big problem. So yeah, I think this would violate many of these criteria. Certainly, error rate parity, for example, is violated. And it's again one of these things where, look, I think the moral intuition that's triggered here is valid, right? We find this like very concerning, and it is, right? And so I don't think they can, in this case, give you a way to mitigate these issues, right? So I think something like sentiment classification or toxicity classification, I think these are very problematic prediction tasks to begin with, just because the target variable is very ambiguous. And I think it's, I know we're working off of the premise that this is what you have to do, but in some sense, I would also like to revisit that premise, because I don't necessarily think that's the right way to phrase these problems. And it runs into these issues. And I don't think these criteria on their own just tell you what to do. I think they would just flag this as an issue, but would not tell you where to go from there. And that's, currently a lot of work in NLP going on what should you do in these cases. Okay. Another question from Aaron. Shouldn't calibration account for individual features to prevent randomization subject to group calibration inside a group? Exactly. So yeah, so this was the example of I had with the orange or the blue group, where you do this kind of averaging operation and you get some undesirable results. The conditional expectation of y given x would satisfy calibration even at the specific feature level. So for every x, this is the condition that you write. That's a much stronger condition. That's basically the condition of optimal prediction. So that's a much stronger setting. And there are papers, that try to, approach this kind of stronger condition related to the subgroup problem. So, I think Gal, who asked the question earlier, has work on that, and Omer Reingold, Guy Rothblum, Michael Kim at Stanford have papers on trying to achieve calibration for richer subgroups, which would approach this kind of stronger guarantee. George is asking, someone earlier touched upon the relationship between acceptance rates and equality of outcome. Can you clarify that relationship, please? Okay, so I will ask the person who asked that earlier to specify what they mean by equality of outcome, and then we can, I feel more confident answering that once we're on the same page about what you mean there. Jan is asking, do you feel it relevant who works, do you feel it? We belong, okay, let me start with the second sentence. We belong to groups and some of us are more privileged than others. How should we consider this? Okay, I would love to also understand your first question, which I can't quite parse. So maybe you can repeat the first question. Oh, do I think it is relevant who, as a matter of identity, who works on these things? Yeah, it is important. I think it's one of these questions where my own perspective as a privileged white man is very limited. And I've worked on formal models from the perspective, from a very limited perspective, right? And I cannot tell, you know, I cannot speak of lived experience of discrimination and oppression. And that's why it is absolutely important to center the voices that can tell you about the lived experience here, right? And that's you know, at the beginning of the talk, I gave you a number of scholars that do that. And I think that's where you should start. I think that's the account of the problem, the account of the experience, and that is absolutely essential. So yes, I think this tutorial should not be your only source on this topic. It's one perspective on the formal and technical work in this area, but by all means, you should not leave it at that. And there's, I think, the way this should work is that we all learn from a number of different sources and from a diverse set of sources, some of them speaking more directly to the lived experiences. And yeah, I think this is an important question. I just realized now that this was a private question. I answered this in public. I hope I didn't, that was not against your intent. Okay, so these are all the questions I can see. I'm also out of time. So it was intended as public. Okay, good.
So Moritz, there was an earlier question by George, and you mentioned that, so George was now among the panelists, maybe he could clarify.
Yeah, hello. I asked about the clarification for quality of outcome. I know it's really close in time, so we can end this now if you want, and I can ask it later.
Why don't we give it a minute? And if
okay, sure. Well, I don't actually know what a quality of outcome sort of means. I'm not like a political person or ethics person. It just sounded important somehow. So this is why I asked for the clarification.
Yeah. Yeah, I think you can think of it as some equality of, you know, outcome. If you think of the outcome as your decision and you're just comparing acceptance rate on that decision, if you sort of, I don't think this criterion captures what a moral philosopher would call equality of outcome. And I think that's probably a longer conversation that we should have later on. But
okay, cool. Do you happen off the top of your head to know of any resources for which that might discuss those two things?
I don't think anybody has attempted to. So this is a good question, right? So this is something my co-author Solon Barocas and I often run into. There's no clear mapping from these criteria to moral philosophy and back. So it's not like, you know, for each criteria you can say, this is the piece of moral philosophy that it's tracking. And I think that's still, we attempted some such, at some point we had high hopes of doing such a synthesis and we didn't get very far. So I don't know if there's probably many people that could give you a better answer, but I don't know from the top of my head of the right paper to look for that exact correspondence or that some such discussion.
Okay, well, thank you very much for that perspective. That does help even identify that it is a big problem.
Yeah, so the correspondence between work and fairness in machine learning and moral philosophy, I think is very unclear to me. I think there's no, that's a good question. If you have colleagues in the philosophy department, that's a good question to chat with them about.
Okay, so thanks a lot, Moritz, for the wonderful lecture. I learned a lot.
Thank you.
And I think everyone also learned a lot from you today. Just a bit of information. So we have a roundtable discussion with Moritz in half an hour. So I guess we can extend some of the discussion to the roundtables. And we have, so before we go for a break, we have short videos, right, from the organizer. So let me show the videos. This one, right?
Yeah. It's good.
Like this?
Yeah.
Yeah, so from my point of view, machine learning is all based on statistical dependencies. So we see that certain quantities are related to other quantities, and then we predict one thing from the other one. Now, usually machine learning doesn't ask where these dependencies come from, and I think they come from underlying causal relationships. And if we're interested in how to do machine learning when certain things in the world change, so when we have training data in one problem, but we are being tested on another problem, which is happening all the time in animals and humans, then it turns out we have to look at things in a little bit more detail. I think this is too complicated, no?
Oh, so this is this is very hard. Okay, I tend to be I'm not really systematic in my research in a sense that I don't wake up on January 1st with an agenda of what I want to do in the next year, and then I just carry out my agenda. So I think a big source of inspiration for me is talking to people that work in industries, cope with hard practical problems that I'm not even aware of. More than reading, it's much more efficient talking to people and understanding what are the important things. I tend to work on things I like, I'm sort of resonate with, as opposed to working on stuff that everybody works on because it's hot. So I am driven a lot by the pleasure in doing research in something that I really find interesting, irrespective to everything else. I didn't want to use the word passionate because being Italian, if I use the word passionate, it sounds a little bit too cliche, but it is true. I mean, I think people should be driven by curiosity and passion because that's a very good driving force, a very healthy driving force.
The best experience is probably the close atmosphere between lecturers and participants. And for me personally, it's of course the opportunity to have attended MLSS 5 years ago and now be a speaker. But the funniest is actually the t-shirt. So when you are outside the ML community, you will often get asked why you attended Miss Tübingen. Because the MLSS reads pretty close to Miss Tübingen.
Okay, thank you very much, everyone. So that would be the end of this session. And so we see you again in 20 minutes or so for the roundtable discussion with Moritz Hardt. Okay, thank you very much and bye-bye.